What if everything you thought you knew about time was just the tip of the iceberg? We live in a universe where scientists have proven time isn't fixed. It warps around black holes, stretches at near light speeds, and might even fold back on itself like a cosmic origami project. Today we're peeling back layers of reality to reveal 25 concepts so revolutionary they'll make you question whether the past is truly behind us or still waiting to be written. From wormholes hiding in plain sight to particles that remember the future, these aren't just thought experiments anymore. Cutting-edge physics suggests our universe might be one grand time machine, with every star and galaxy holding clues to journeys we've barely begun to imagine. The most shocking part, some of these temporal doorways could be within our reach sooner than anyone predicted. Imagine stepping through a hidden doorway that warps you across the galaxy, or even centuries into the past. Wormholes aren't just sci-fi fantasy, they're rooted in Einstein's equations woven into the fabric of spacetime itself. Picture space as a stretched bedsheet. Fold two distant corners together, and suddenly a shortcut appears between them. That's the essence of a wormhole, a cosmic tunnel linking points that would otherwise take billions of years to reach. But here's the catch: these space-time shortcuts are incredibly unstable. Like a soap bubble about to pop, they'd collapse instantly without something exotic holding them open. Think matter with negative energy, a bizarre quantum phenomenon that defies gravity. Recent breakthroughs suggest quantum entanglement. Those spooky connections between particles might provide the glue to stabilize these tunnels. Yet even if we could build one, stepping inside would be a gamble. A single misstep, a stray photon, and the wormhole snaps shut like a cosmic bear trap, leaving any would-be time travelers stranded. Does this mean wormholes are just mathematical mirages? Not necessarily. Black holes were once deemed theoretical oddities too until we photographed one. The same could happen with wormholes. Some physicists speculate they might already exist, hidden in plain sight, disguised as black holes or lurking in the quantum foam of spacetime. The real question isn't whether they can exist, but whether we'll ever unlock their secrets or if some ancient civilization already has. What if the universe secretly hid roads that loop back in time like cosmic Möbius strips, closed time-like curves first dreamed up by mathematician Kurt Gödel, are exactly that strange pathways where spacetime bends so severely that traveling forward inevitably brings you back to your own past? Picture walking along a treadmill that somehow loops you to the moment you first stepped on. That's the eerie magic of these relativistic loops, where cause and effect start tying themselves in knots. Einstein's equations show these time loops could form naturally under extreme conditions, perhaps near a rapidly spinning black hole, where space and time twist like water circling a drain. Yet here's where things get unsettling. If you followed one of these loops and, say, stopped your parents from meeting, the paradox would unravel existence itself. Some physicists argue quantum mechanics might smooth out these contradictions like a cosmic referee, ensuring no rule breaking, while others insist nature slams the door on such paradoxes entirely. The debate hinges on one crucial question: does the universe guard causality like an unbreakable law, or does it allow wiggle room for time travelers to dance along its edges? Recent experiments with quantum particles show hints of retrocausality affects preceding causes, suggesting reality might be far more flexible than we thought. Whether closed time-like curves exist or not, they force us to confront a spine-tingling possibility. The past might not be as fixed as it seems. Here's the next segment of the script. Scientists once thought quantum entanglement was bizarre enough, particles whispering to each other instantly across vast distances, defying the speed of light. But what if this eerie connection doesn't just bridge space but time itself? Imagine tossing a coin into a wishing well. only to watch it ripple backward through the water before it even leaves your hand. That's the mind-bending idea behind temporal entanglement, where events in the future might reach backward to tweak the past. In labs around the world, physicists are stacking the deck with delayed choice experiments, tests where decisions made now seem to rewrite what already happened. Picture a cosmic game of billiards where the final shot changes where the balls were moments earlier. These experiments don't just hint at retrocausality, they suggest time might operate like a tangled network where past and future constantly negotiate reality. The implications are staggering. If particles in the present can be entangled with their own future states, does that mean destiny is negotiable? Or is the universe simply working in ways our linear brains can't fully grasp? Some theorists argue this could be the missing link for time travel, nature's cheat code for stitching together timelines without paradoxes. Others warn it might unravel causality entirely, turning history into a choose-your-own-adventure book where every page affects the ones before it. One thing's certain, if entanglement truly spans time, then the rigid past-present-future we know might be nothing more than an illusion, a flickering hologram projected by something far stranger. What if you could build a time machine simply by spinning a cosmic column fast enough to twist the fabric of reality itself? Physicist Frank Tipler proposed exactly that, a cylinder so massive and spinning so furiously that it doesn't just bend spacetime, it ties it into knots. Imagine dropping a stone into a whirlpool, watching the water curl back on itself. Now replace the water with time itself, and you've got the essence of Tipler's cylinder, a colossal spacetime vortex where the future loops into the past. To make this work, you'd need a cylinder stretching infinitely through space, spinning at nearly the speed of light. The sheer rotational energy would drag spacetime along with it, like honey clinging to a spinning spoon. The math suggests that if you circled this cylinder in just the right way, you could follow a path that spirals backward through time. No exotic matter, no wormholes, just raw centrifugal force warping causality into a pretzel. But here's the catch: building it defies known physics. The cylinder would need to be impossibly dense, made of materials that don't exist, or at least that we haven't discovered yet. And that's before accounting for the energy required, which could dwarf the output of entire stars. Still, the idea isn't just science fiction. It forces us to ask a profound question. Is time travel blocked by nature's laws or just our current engineering limits? Some theorists argue that advanced civilizations, millions of years ahead of us, might have cracked the code, weaving space-time into megastructures we can't yet fathom. Others counter that if such cylinders were possible, we'd see evidence of them littering the cosmos, unless, of course, their builders erased their own tracks. Either way, Tipler's cylinder does something remarkable. It turns time travel from a question of if into a puzzle of how, and that changes everything. Here's the next segment of the script. Ever felt like the universe has an invisible hand guiding events, making sure everything fits together just right? The Novikov self-consistency principle takes that idea and cranks it up to cosmic levels. Picture time as a meticulously crafted puzzle. Every piece, every event slots together so perfectly that any attempt to force a contradiction simply won't fit. According to Russian physicist Igor Novikov, time travel wouldn't be a free-for-all of rewriting history. Instead, the universe would act like a relentless editor, trimming away any actions that could create paradoxes before they ever happen. Take the classic grandfather paradox. If you traveled back and tried to prevent your own birth, anything would intervene. A gun jams, a missed train, a sudden change of heart. The timeline wouldn't allow it. No loopholes, no contradictions, just an unbreakable chain of cause and effect. Recent quantum experiments even hint at this eerie self-correction. Particles seem to choose paths that avoid paradoxes, as if reality itself has a failsafe against its own unraveling. But this raises a chilling question. If the timeline is that rigid, does free will even exist for time travelers? Or are their choices just illusions predetermined by the universe's need for consistency? Some argue this principle doesn't kill free will, it just means our decisions align seamlessly with the past, like actors improvising within a script they didn't know they were following. Others counter that it turns time into a prison where every move was always destined to happen. The real tension lies in what this says about causality itself. Is the universe bound by unshakable rules, or is there wiggle room we haven't discovered yet? If Novikov is right, time travel wouldn't be a tool for rewriting history, just a way to witness how perfectly the threads of reality are already woven together. Stephen Hawking once joked that the absence of tourists from the future might be the strongest evidence against time travel, but his chronology protection conjecture was no laughing matter. Imagine the universe as a meticulous security system, armed with quantum tripwires that detonate any attempt to breach the timeline. According to Hawking, the moment you tried to open a doorway to the past, vacuum fluctuations, those ghostly particles popping in and out of existence, would amplify catastrophically, unleashing an energy surge powerful enough to collapse the time tunnel like a house of cards in a hurricane. Yet nature rarely deals in absolutes. While Hawking's idea paints time travel as a cosmic impossibility, some physicists argue his conjecture might have blind spots. Certain exotic spacetime geometries, like traversable wormholes stabilized by negative energy, could theoretically slip past this quantum defense mechanism. Others propose that black holes already known to warp time beyond recognition might harbor natural loopholes where chronology protection fails. The debate hinges on a deeper mystery. Is the universe actively preventing time travel, or are we just underestimating its ingenuity? Recent quantum experiments show particles briefly defying classical causality, hinting that reality might tolerate small temporal anomalies if they don't spiral into paradoxes. It's possible Hawking's shield isn't an ironclad law, but more like immune system, one that attacks only threats severe enough to disrupt causality. So is the past truly locked away, or are we simply missing the key? The answer might lie in the gray zone where quantum weirdness dances with relativity. One thing's certain: if time travel is possible, it won't be as simple as flipping a switch. The universe seems determined to make us earn every second. Here's the next segment of your script. Think of the most precise clock ever built, one that doesn't just measure time but repeats it like a cosmic drumbeat. That's the essence of a time crystal, a strange form of matter that breaks one of physics' oldest rules, the arrow of time. Unlike traditional crystals, whose atoms arrange in repeating patterns in space, time crystals rhythmically rearrange themselves in time, snapping back to their original state over and over without losing energy. It's as if you dropped a snowflake into water, only to watch it reform every few seconds, untouched by entropy's relentless pull. When Nobel laureate Frank Wilczek first proposed them in 2012, critics dismissed the idea as fanciful. How could anything move perpetually without an energy source? Yet by 2017, labs had created them using chains of ions or defects in diamonds, proving these structures weren't just theoretical quirks, they were a new phase of matter. The secret lies in quantum entanglement, which locks particles into a synchronized dance where they're forever out of step with time itself. The implications are staggering. Time crystals don't just challenge thermodynamics, they hint at a universe where matter can remember cycles of time. Imagine a clock powered not by gears but by these quantum echoes, ticking reliably across alternate timelines or even in the vacuum of space. Some theorists speculate they could anchor future technologies like quantum computers that process information by cycling through states in the fourth dimension. Others wonder if there are evidence of deeper temporal symmetries woven into reality itself. But here's the twist: time crystals aren't time machines. They can't send you to the Renaissance or predict next Tuesday's weather. What they do is something perhaps more profound. They prove time isn't just a backdrop to the universe. It's a material that can be folded, shaped, and maybe one day harnessed. If crystals in space give us silicon and diamonds, what might crystals in time eventually unlock? The answer could rewrite physics, not just in theory, but in the very fabric of our clocks, computers, and understanding of existence. Here's your next segment. Picture standing at a crossroads where every possible path isn't just imagined, it's real. According to the many worlds interpretation, each choice you make doesn't just alter your future. It splits the universe into parallel versions, each playing out every conceivable outcome. Now drop time travel into this quantum kaleidoscope. Instead of rewriting history, you'd simply step sideways into a brand new timeline, leaving your original past untouched. It's like hitting save as on reality. Your old world stays intact while you forge ahead in a fresh, unspoiled copy. This idea solves one of time travel's biggest headaches, paradoxes. Kill your grandfather, you're not erasing yourself, you've just branched into a universe where his death creates a new, self-consistent future. The laws of physics stay happy and causality remains unbroken. Quantum experiments even hint at this possibility. Particles seem to sample multiple paths simultaneously, as if testing alternate realities before settling into one. But here's where things get wild. If every decision spawns new worlds, there must already be infinite versions of you out there. Somewhere you're an astronaut, somewhere else you never existed at all. Yet the many worlds approach raises haunting questions. If you jump timelines, could you ever find your way back? Or would you wander forever through ever-branching realities, each step taking you further from home? Some theorists argue these branches might subtly interact, creating faint echoes between worlds like déjà vu or dreams that feel too real. Others insist once a timeline splits, it's sealed off completely, making return trips impossible. The most unsettling implication isn't about technology, it's about identity. If countless versions of you are living different lives, which one is really you? The answer might rewrite not just how we see time travel, but how we define existence itself. What if breaking the cosmic speed limit wasn't about going faster, but about bending the road itself? That's the radical premise behind the Alcubierre warp drive, a concept that treats spacetime like stretchy fabric. Instead of pushing a ship through space at impossible speeds, this theoretical engine would crumple the space ahead while smoothing it out behind, creating a bubble where the craft rides undisturbed, like a surfer gliding on a wave that's rewriting the shorelines of reality. Inside this warp bubble, time would slow relative to the outside universe, effectively catapulting passengers into the future without aging them a second. Miguel Alcubierre's 1994 proposal seemed like elegant magic. No faster than light travel through space, just clever manipulation of space. But the devil's in the details, specifically the negative energy required to sustain the warp field. This exotic substance would defy gravity, repelling rather than attracting matter. While quantum physics hints that negative energy might exist in microscopic amounts, scaling it up to power a starship is like trying to light a city with a single match. Yet hope isn't lost. Recent breakthroughs in modified gravity theories suggest we might not need unobtainium after all. Certain adjustments to Einstein's equations, like those incorporating higher dimensions or dark energy analogues, could theoretically generate warp effects without negative energy. Supercomputer simulations have even modeled stable warp bubbles under these conditions, though the energy requirements still dwarf anything humanity can produce. The ultimate question isn't just whether warp drives are possible, but what their existence would mean. A functional Alcubierre engine wouldn't just be a ticket to Proxima Centauri, it'd be a time machine. Arrive at a distant star in months and centuries could have passed on Earth. This forces us to confront a haunting trade-off. The farther we voyage, the more we sever ties with everyone we've ever known. Perhaps that's the true barrier, not physics, but psychology. Are we ready to surf the wrinkles of spacetime if it means outpacing time itself? The answer may determine whether we remain earthbound or become the time travelers of tomorrow. Here's your next segment. Gravity doesn't just bend space, it twists time like taffy, and nowhere is this more extreme than at the edge of a black hole. Picture an astronaut orbiting just outside the event horizon, where gravity's grip is so fierce that time slows to a crawl. For them, minutes tick by, but back on Earth, centuries vanish in a blur. This isn't science fiction, it's Einstein's general relativity in action, and we already account for it every day. The GPS in your phone constantly adjusts for time dilation caused by Earth's gravity, though the effect is microscopic compared to the warping near a black hole. But harnessing this effect as a time machine comes with brutal trade-offs. Even if you could withstand the gravitational tides trying to spaghettify your body, the energy required to reach such an extreme environment, let alone escape it, would dwarf anything humanity has ever produced. The closest black hole, V616 Monocerotis, is still 3,000 light-years away. By the time you return from even a brief orbit, Earth might be unrecognizable or gone entirely. Yet black holes aren't the only way to exploit this phenomenon. Neutron stars, the dense remnants of supernova, also warp time significantly. Hypothetically, if you could orbit one safely, you might skip decades forward with each loop. Some physicists speculate about artificial gravity wells, future technologies that mimic these conditions in controlled settings, like a particle accelerator for time itself. The catch, the energy needed might require tapping into stars or harnessing dark matter. The real lesson of black hole time dilation isn't just about extreme physics, it's about relativity's quiet power in our daily lives. Time flows differently for satellites, mountaintops, even your feet versus your head. Black holes magnify this truth to cosmic proportions, forcing us to ask, is time travel about finding loopholes or just learning to ride the currents that already exist? The answer might rewrite not just our future, but our understanding of now. Here's your next segment. History tells us Shakespeare penned Hamlet in the early 1600s, but what if the truth is stranger? Imagine a time traveler handing the bard a complete folio of his future works, sparking a chain where the plays were never truly written, just endlessly recycled across centuries. This is the Bootstrap Paradox, a dizzying loop where cause and effect chase each other like a dog biting its own tail. The chilling part, there's no origin point, just information or objects that seem to materialize from thin air, trapped in an infinite cycle of their own existence. Think of it as a cosmic version of finding your smartphone in a medieval tomb. If you take it home, then eventually invent identical tech centuries later, who actually created it. The paradox isn't just a thought experiment, it exposes a crack in our understanding of linear time. Some quantum physicists argue these loops might unravel naturally, with tiny fluctuations introducing enough randomness to break the cycle. Others propose their evidence time isn't a straight line, but a tangled web where past and future constantly rewrite each other. Real-world mysteries fuel these debates. Take the Antikythera mechanism, an ancient Greek device with gears too advanced for its time. Could it be a relic from a future civilization lost in history? Or consider certain mathematical theorems rediscovered independently across eras, echoes of knowledge slipping through time's cracks. The Bootstrap Paradox forces a haunting question. Are there ideas, inventions, even people in our history who exist without a true beginning? If so, time isn't just something we move through. It might be something we're actively stitching together, thread by thread, with every choice we make. Here's your next segment. We think of time as a river always flowing, never stuttering. But what if that's an illusion? At the tiniest scales imaginable, time might not be smooth at all. Instead, it could tick forward in discrete quantized jumps, like the individual frames of a movie reel too fast for our senses to detect. This is the startling idea behind quantum time theory. That reality has a hidden frame rate, with each quantum frame lasting roughly 10 to the power of -43 seconds, a span so short, 1,000,000,000,000 of these moments pass in the blink of an eye. Think of it like flipping through a flipbook. At normal speed, the images blur into motion, just as our brains stitch time's quantum frames into a seamless flow. But if you could pause or rewind the book frame by frame, you'd see the gaps between moments. Some physicists argue this might be possible in principle, that time travelers wouldn't slide smoothly through history, but jump between these frozen instants like a DVD skipping scenes. The wildest part, we're already testing this. Atomic clocks precise enough to lose just 1 second every 15 billion years are hunting for evidence that time stutters at the quantum level. If they detect subtle irregularities, tiny hiccups in the rhythm of reality, it could confirm the universe runs on a cosmic refresh rate, and that opens doors to technologies we've barely dreamed of. Imagine devices that don't just tell time, but manipulate its very pixels, rewinding or fast-forwarding those frames like editing a video, yet skepticism remains. If time is digital, what governs its frame rate? Is there a processor behind existence, or does it emerge from deeper physics? Opponents argue smooth time fits Einstein's equations too elegantly to discard. But if quantum time is real, it wouldn't just revolutionize time travel, it'd mean everything we experience, from thoughts to supernova, is underpinned by something far stranger. A universe that renders reality moment by moment in the smallest increments possible. One thing's certain, whether time flows or flickers, our understanding of it is still in its earliest frames, and the next clue might come from a lab bench or from the universe itself, ticking away in quantum silence. The most chilling time travel stories aren't about changing history, they're about realizing you were always part of it. Picture a doctor rushing to prevent a deadly epidemic, only to discover their own actions caused the outbreak. That's the predestination paradox in action, a twisted dance where every attempt to alter events just locks them into place. It's like trying to erase a shadow by shining a light. The harder you fight, the darker it becomes. Einstein's equations allow for these loops mathematically, but the real-world implications are unnerving. Take the infamous case of John Titor, an online poster claiming to be a time traveler from 2036. He shared technical details about his time machine, details that later inspired real-world researchers. If his account was fiction, it's an eerie coincidence. If genuine, it suggests even warnings about the future might create that future. Quantum physicists call this post-selection, a subtle pressure nudging timelines toward consistency. Yet there's a glimmer of hope buried in the madness. Some theories propose these loops aren't perfect prisons. Tiny quantum fluctuations could introduce enough randomness for escape routes. Think of a DVD skipping slightly, allowing a new scene to emerge. Experiments with entangled particles show they occasionally forget their predetermined paths, hinting that reality might have loopholes after all. The real question isn't whether we're trapped in cosmic scripts, but how much divergence the universe tolerates. If predestination is real, it's not a chains, it's a river with countless currents. Navigating them might not rewrite history, but it could reveal how deeply we're woven into its fabric. What if black holes aren't cosmic in points at all, but just one side of a tunnel leading somewhere far stranger? Enter white holes, the hypothetical twins of black holes where gravity's rules flip inside out. Picture a black hole in reverse instead of pulling everything in with unstoppable force. A white hole violently expels matter and energy like a cosmic geyser erupting into existence. According to some solutions to Einstein's equations, these entities could be the other end of a black hole spacetime tunnel, spitting out whatever fell in long ago, but not necessarily in the same when. Unlike their dark siblings, white holes can't be entered, only exited. That's because their event horizons act like one-way doors, pushing outward with such intensity that nothing can cross back inside. Theoretically, if you fell into a black hole and survived its crushing depths, you might be flung out of a white hole into another time, another universe, or even another dimension. The catch: white holes should be spectacularly bright. Imagine the energy of an entire star's collapse fired like a cannon into space, yet we've never spotted one. So why do physicists keep searching? Because their existence would solve two cosmic mysteries at once. First, it'd mean black holes don't destroy information, a violation of quantum rules, but instead recycle it elsewhere. Second, it'd imply our universe might be dotted with invisible time warps, where matter from ancient eras or distant realities suddenly bursts into our present. Some fringe theories even suggest gamma-ray bursts, those violent flashes in deep space, could be dying gasps of white holes flickering into oblivion. But here's the real puzzle: if a white hole did appear in our solar system, would we recognize it? Its light would be oddly time-reversed, like watching a supernova explode in reverse. Particles ejected might carry signatures of long-dead stars or unfamiliar physics. And the gravitational waves it produced, they'd ripple through space like echoes from a future or past we've never seen. The unsettling truth is that white holes might not be permanent. Some models suggest they'd evaporate instantly, their energy bleeding out in a flash of paradoxes. Others argue they could stabilize in the right conditions, becoming cosmic fountains spraying spacetime itself into new geometries. Either way, their mere possibility forces us to rethink the darkest corners of the universe, not as graves for matter, but as doors waiting to be pushed open from the other side. Imagine your entire life, every memory, every moment, could be encoded on a flat surface like a cosmic DVD containing the blueprint of reality. This isn't sci-fi. It's the essence of holographic theory, a mind-bending idea suggesting our three-dimensional universe might just be a projection of data stored on a two-dimensional boundary at the edge of existence. Even stranger, time itself could be nothing more than an illusion emerging from how that data is processed, like pixels flickering to life on a screen. Think of it this way: a hologram encodes a 3D image on a flat surface, and when lit just right, the full depth appears. Now scale that up to universal proportions. The screen could be the event horizon of our cosmos, a surface where information about everything inside it is mysteriously imprinted. Time, in this view, isn't a fundamental force but a side effect of how that information is decoded, frame by frame. Tweak the data and you might rewrite history itself, not by traveling through time but by editing the source code of reality. The implications are staggering. If holographic theory holds, black holes could be nature's hard drives, their event horizons storing unimaginable amounts of compressed data. Experiments with quantum gravity already hint at this. When calculating the entropy of a black hole, physicists found it scales with its surface area, not its volume, exactly what holography predicts. Even our own brains might operate like mini holograms, with memories and consciousness emerging from layered information patterns. But here's the twist: if time is just data processing, could we hack it? Some theorists speculate that advanced civilizations might manipulate spacetime by rewriting these cosmic pixels, folding time like a programmer debugging a simulation. Others warn that tampering could unravel causality itself, collapsing the illusion into chaos. The real question isn't just whether we live in a hologram, it's whether time is a river we sail or a script we're inside. And if the latter, who or what is holding the pen? What if the ticking of every clock isn't tracking some fundamental force, but just counting the ripples of something deeper? A growing number of physicists are questioning whether time exists at all in the way we experience it. Instead, they propose it emerges from the chaos of quantum interactions, much like temperature isn't a thing itself but a measure of atoms jostling in frenzy. Think of it this way: a single molecule doesn't have a temperature, just speed, but gather trillions and suddenly warmth appears as a collective effect. Time might work the same way, a cosmic mirage conjured by particles interacting in ways we're only beginning to glimpse. At the heart of this idea lies quantum entanglement, where particles become so deeply linked that measuring one instantly defines the other, no matter the distance. Experiments show these connections don't just bridge space, they seem to blur the line between cause and effect. In labs, particles sometimes behave as if they're reacting to events before they happen, as if time's arrow is just a suggestion. This has led to wild theories. What if now isn't a universal moment, but a patchwork of quantum relationships stitching reality together? The implications for time travel are staggering. If time emerges from these interactions, mastering them could let us reweave its fabric without paradoxes. Imagine not moving through time but reconfiguring it by altering the quantum states that generate its illusion. Some researchers are already testing this with quantum simulators, devices that model how time-like behavior pops up in controlled systems. Early results hint that under certain conditions, time's flow can literally pause or reverse locally, like eddies in a river. Yet skeptics push back. If time isn't fundamental, why does it feel so relentless to us? The answer might lie in entropy, the universe's tendency toward disorder. Even if time is emergent, the arrow of entropy gives it direction, like a one-way street painted over quantum chaos. That's why we remember the past but not the future, why cause precedes effect. But here's the twist: in rare quantum systems, entropy can briefly decrease, creating what appear to be microscopic time loops. So is time real, or just a convincing collective hallucination? The answer could redefine not just time travel, but reality itself. If the flow of existence is more like a symphony tuning itself than a river flowing, we might not need time machines, just the right key to change the music. Concept 17. The Fermi paradox and time travel. The universe should be teeming with life, mathematically speaking. With billions of habitable planets, why does the cosmos feel so empty? This is the Fermi paradox, and it gets even stranger when you throw time travel into the mix. If crossing centuries is possible, where are the chrono-tourists snapping pictures of dinosaurs or elbowing their way into historical events? Their absence might be the biggest clue yet about the nature of time itself. One unnerving possibility is that time travelers are here, just undetectable. Imagine a civilization so advanced it treats historical observation like a cosmic nature reserve. They'd have protocols to avoid contamination, studying us the way biologists study ants, careful not to disturb the colony. Or worse, what if their very presence creates branching timelines, leaving our version of history untouched while they explore parallel realities we'll never see? Then there's the darker interpretation. Maybe civilizations capable of manipulating time don't survive their own power. The same breakthroughs that unlock temporal travel could also weaponize causality, turning history into a battleground. A single rogue time traveler might erase entire eras, collapsing civilizations before they ever reach the stars. It's a chilling thought that the great filter keeping the universe silent isn't asteroids or supernova, but time travel itself. Yet some physicists propose a subtler answer. If traversable wormholes or warp drives require conditions we haven't discovered, like exotic matter or energies beyond our grasp, then the universe might allow time travel in theory but make it impossibly rare in practice. The cosmos could be littered with the ruins of civilizations that burned out trying to crack the code, their failed experiments lost to black holes or quantum collapse. The silence of the stars might not be a no to time travel but a caution sign. Every quiet light in the night sky could be whispering, some doors once opened can't be closed. Whether that's a warning or a challenge depends on how far we're willing to reach and what we're willing to risk to meet our future selves in the dark. Concept 18. The butterfly effect in time travel. A single misplaced footstep could rewrite history, not with a dramatic explosion or a grand declaration, but with something as small as a crushed leaf, a disturbed pebble, or a breath of air moving differently. This is the terrifying heart of the butterfly effect, where even the slightest change in the past could send shockwaves through time, transforming the present beyond recognition. Chaos theory tells us reality is a house of cards. Tweak one corner, and the entire structure might collapse. Picture this: a time traveler walks through a prehistoric forest, unknowingly brushing against a fern. That tiny disturbance alters the path of a single insect, which then fails to pollinate a plant. Fast forward millions of years, and that plant's absence reshapes entire ecosystems, leading to a world where humanity never evolves. What seems trivial in the moment becomes a cosmic domino effect, erasing civilizations before they even begin. The frightening truth: there's no undo button. But here's where physics gets strange. Some theories propose the universe might have a self-correcting mechanism, like a rubber band snapping back when stretched too far. Quantum fluctuations or hidden laws of causality could dampen minor changes before they spiral out of control. We see hints of this in nature. Certain systems resist chaos, like how rivers return to their courses after minor disturbances. Could time have similar safeguards? The real challenge lies in prediction. Even with perfect knowledge of every atom in the past, chaos theory suggests that forecasting long-term consequences is impossible. Tiny errors multiply exponentially, turning any attempt at safe time travel into a gamble with reality itself. Some scientists speculate that advanced civilizations might use quantum simulations, testing changes in virtual timelines before risking the real thing. Others argue the only foolproof rule is to never interact with the past at all. So, is time tourism doomed to be a destructive force? Or could we one day master history like master editors, tweaking scenes without unraveling the entire film? The answer might define not just the future of time travel, but whether we dare to reach into the past at all. One wrong move and the world we know could vanish like a whisper in the wind. Concept 19. The grandfather paradox. Revisited. Every time traveler's worst nightmare isn't facing prehistoric beasts or getting stuck in the Middle Ages. It's the horrifying moment they realize their own existence hinges on doing nothing. The classic grandfather paradox is mercilessly simple. Go back, prevent your grandfather from meeting your grandmother, and suddenly your family tree and you fade from history like a photograph left in the sun. But what if the universe has a workaround? Emerging theories suggest causality might not break so easily. It just gets a lot weirder. Take parallel timelines. Instead of erasing your own past, any change you make could branch reality into a new thread, one where your grandfather dies, but your original timeline remains untouched. You wouldn't vanish, you just become a refugee from a version of history that no longer includes you. Quantum physics offers an even stranger twist. Until someone observes the outcome, your grandfather exists in a superposition, both alive and dead, like Schrödinger's cat in a time loop. Only when the timeline checks does it settle into a single state, potentially sidestepping the paradox entirely. But here's where the debate ignites. If every decision spawns alternate worlds, does time travel lose its meaning? You're not rewriting history, just hopping between pre-written drafts, and quantum solutions raise their own riddles. Who or what counts as the observer that collapses these possibilities into reality? Some argue consciousness itself might play a role, tying time's behavior to the minds witnessing it. Others insist the universe enforces consistency through hidden laws we've yet to uncover. The real shock isn't just that these theories exist, it's that they're being tested. Quantum labs have already created microscopic scenarios where particles seem to choose histories that avoid paradoxes, as if reality self-censors to stay logical. If scaled up, this could mean time travelers aren't bound by chains of causality, but by something far subtler, a cosmos that edits itself on the fly to keep the story coherent. So, is the grandfather paradox a dead end or a doorway? The answer might not just reshape time travel, it could reveal whether the universe runs on fixed rules or improvises as it goes. Either way, one lesson is clear: tampering with time isn't just dangerous, it's a mirror showing us how little we truly understand about the fabric of reality. Concept 20. Time travel via cosmic strings tucked away in the fabric of the universe might be cosmic threads so dense they twist spacetime itself into knots. These aren't metaphors, they're cosmic strings, theoretical cracks in reality formed during the universe's violent birth. Thinner than an atom yet stretching across light years, they'd carry unimaginable mass, bending space and time around them like invisible whirlpools. And here's the mind-bending part. If you could swing a ship around one at near light speed, you might not just travel through space, you could loop back through time. Picture a cosmic string as a wrinkle in a tablecloth. If you could skate along its edge just right, the warped spacetime would let you outrace causality itself. Einstein's equations suggest this wouldn't just be a shortcut, it'd be a temporal slingshot, where each loop around the string flings you further into the past. No exotic matter, no wormholes, just pure relativistic physics bending time into a pretzel. The catch: these strings, if they exist, would be vanishingly rare, drifting through the void like ghostly leftovers from the Big Bang. Yet the math is tantalizing. Calculations show even a single cosmic string, moving at relativistic speeds, could create closed time-like curves, those paradoxical loops where cause and effect start spinning in circles. Some theories propose these strings might have sparked the universe's most asymmetric structures, like quirks in the cosmic microwave background or unexplained gravitational waves. If we ever detected one, it wouldn't just rewrite cosmology, it'd hand us a blueprint for engineering time machines. But here's where theory collides with practicality. Harnessing such an object would demand precision beyond anything we've ever attempted. A stray encounter with a string's gravitational field could shred matter into spaghetti, and the energy needed to navigate it would dwarf our planet's entire output. Still, the possibility lingers like a dare. If nature tied these knots into spacetime, someone or something might have already found a way to pull them open. The most haunting question isn't whether cosmic strings exist. It's whether we're alone in realizing their potential, or if, somewhere in the dark, another civilization has already threaded time's needle. Concept 21. The quantum Zeno effect and frozen time. There's an old saying that a watched pot never boils. But what if that's not just a quirk of impatience, but a hidden law of reality? In the quantum realm, this turns out to be shockingly literal. The quantum Zeno effect reveals that simply observing a particle can halt its decay, like pressing pause on its natural evolution. The more frequently you measure it, the more it resists change, as if reality itself hesitates under scrutiny. Now, take that eerie phenomenon and scale it up. Could we, in theory, slow or even freeze time itself just by looking at it closely enough? At the heart of this idea lies one of quantum mechanics' strangest quirks. Every time we measure a particle, its wave function collapses, essentially resetting its quantum clock. Bombard it with constant observations and it barely has a chance to evolve at all. Labs have already demonstrated this with unstable atoms, keeping them from decaying far longer than nature normally allows. The unsettling implication, time's flow might not be an inexorable force, but something far more fragile, a process that bends under the weight of attention. But here's the catch. Applying this to the macroscopic world isn't just difficult, it borders on fantasy. To freeze even a speck of dust for a second would require trillions of observations per instant, an energy demand that could outstrip the sun's lifetime output. And that's before grappling with the measurement problem. What even counts as an observation? Does a machine suffice, or does it take a conscious mind? Some theories suggest the universe itself might act as a perpetual observer, enforcing time's flow like an unstoppable metronome. Yet the Zeno effect offers a profound clue. If time can be slowed by observation at the quantum level, perhaps its apparent continuity is an illusion, a cascade of tiny freezes and jumps too rapid for us to perceive. Think of it like a strobe light flickering so fast the motion seems fluid. This would mean time isn't a river, but more like a flipbook with reality refreshing itself moment by moment. So could we ever harness this to pause time? Probably not in the way sci-fi dreams of, but the deeper lesson isn't about control, it's about connection. The Zeno effect blurs the line between observer and observed, suggesting that time might not pass around us but through us. In a universe where watching changes the watched, we're not just passengers on the clock's ticks, we're participants shaping time even as it shapes us. The real mystery isn't whether we can stop time, it's whether it was ever truly moving on its own to begin with. Concept 22. The pulsar time capsule. Deep in the cosmic dark, celestial metronomes keep perfect time. Pulsars, the dense, spinning cores of dead stars, fire beams of radiation across space with such precision they rival Earth's most advanced atomic clocks. These cosmic lighthouses flash with unshakable regularity, some ticking for millennia without missing a beat, and that consistency holds an extraordinary possibility. What if we could encode messages in their pulses, turning these stellar relics into time capsules for civilizations thousands or even millions of years from now? Here's how it could work. Just as Morse code uses patterns of dots and dashes, scientists could alter a pulsar's natural rhythm in deliberate ways, perhaps by nudging it with precisely timed energy beams or placing reflective satellites in its path. The resulting changes in its pulse frequency would carry information like grooves on a vinyl record spinning through the ages. Future astronomers decoding these subtle variations might uncover everything from star maps to warnings about cosmic hazards, or even a greeting from a species long gone. Of course, the challenges are staggering. Modifying something as massive as a neutron star would require technology far beyond our grasp today. The energy needed to influence a pulsar's spin is unimaginable, and any interference would need to be subtle enough not to disrupt its natural stability. But here's the beauty of the idea. Even unmodified pulsars already act as natural timekeepers. Civilizations separated by eons could use them as universal reference points, synchronizing calendars across galactic history by noting the exact moment a pulse arrives. This raises a haunting question. If pulsars are such perfect time capsules, why haven't we found any with obvious signs of tampering? Maybe the universe is too vast and we've simply not looked closely enough. Or perhaps advanced civilizations choose subtler methods, embedding data in ways we're not yet equipped to recognize. Some astronomers even speculate that certain anomalous pulsars, ones with inexplicable glitches or rhythms, might already be carrying messages we can't yet decipher. The pulsar time capsule isn't just about reaching the future, it's a test of our own foresight. If humanity vanished tomorrow, would our signals linger in the cosmos, waiting for someone to listen? Or would the universe's natural rhythms outlast us, indifferent to our attempts to etch our stories into the stars? Either way, pulsars remind us that time isn't just something we move through. It's something we might one day learn to speak through in beats as old as the universe itself. Concept 23. Dark energy and the arrow of time. Most of us take for granted that time moves forward. Eggs don't unscramble and memories don't unform. But what if that's only true for now? The universe's accelerating expansion, driven by the enigmatic force we call dark energy, might hold the key to time's stubborn one-way flow. And if dark energy changes over eons, the arrow of time could flip, unraveling the very fabric of cause and effect. Think of dark energy as the universe's unseen fuel, stretching space itself faster and faster, pushing galaxies apart. This expansion seems to steer time's direction by increasing entropy, the measure of disorder that gives our lives their irreversible sequence. But here's where the plot thickens. If dark energy weakens or transforms, the cosmos might stop accelerating, even collapse inward in a big crunch. In that scenario, entropy could reverse and time itself might run backward, at least from a cosmic perspective. You wouldn't suddenly see broken cups reassemble, but the entire universe could, in theory, rewind toward its birth. Some physicists argue this isn't just speculation. Quantum gravity models hint that dark energy might not be constant. It could decay, fluctuate, or even shift into a new state. If that happens, the fate of time itself hangs in the balance. Imagine a distant future where stars don't just fade, but unburn their fuel, where black holes spit out swallowed matter, and the cosmos retraces its steps toward a singularity. It's a dizzying thought, history not as a straight line, but as a cosmic pendulum swinging between creation and destruction. Yet skeptics counter with a simpler answer: time's arrow might be locked in place. Even if dark energy evolves, entropy could have a built-in bias, like a ratchet clicking only forward. Experiments with quantum particles show that while tiny systems can temporarily defy entropy's pull, large-scale reversals seem impossible without rewriting physics itself. The real mystery isn't just whether time could reverse, but whether the universe cares. If dark energy is the conductor of this grand temporal symphony, we're only hearing the opening notes. The final movement, whether it's a rewind, a repeat, or an ending we can't yet imagine, might depend on forces deeper than time itself. And that leaves us with a humbling thought. The arrow we follow so faithfully may not be ours to control, only to witness. Here's your next segment. Glitches in the Matrix aren't just Hollywood fiction, they might be clues that reality itself is running on borrowed time. The simulation argument, first proposed by philosopher Nick Bostrom, suggests our universe could be an artificial construct, an advanced civilization's cosmic sandbox. And if that's true, time travel might not involve wormholes or warp drives at all. It could be as simple as reloading an earlier save point, like hitting undo on a cosmic keyboard. Think of it like playing a video game. If you stumble into a pit, you don't rebuild the level, you just restart from the last checkpoint. In a simulated reality, time travel might work the same way. A reset button pressed by the universe's architects, or even accidental rollbacks caused by system errors. This could explain eerie phenomena like déjà vu, those moments when life feels unnervingly familiar, as if we've lived them before. What if we have, not in some past life, but in a previous iteration of the simulation, where events played out just slightly differently? But there's a catch. Just as game developers impose rules to prevent cheating, simulation programmers might enforce strict limits on time manipulation. Too much tampering could corrupt the entire construct, like a computer crashing from overloaded memory. That could be why paradoxes feel impossible. They're not forbidden by physics, but by firewalls. Some theorists even speculate that quantum indeterminacy, The randomness at the heart of particles' behavior isn't randomness at all. It's the simulation's way of randomizing outcomes to prevent time travelers from exploiting predictable patterns. Yet not all researchers buy into this digital dystopia. Critics argue that simulating an entire universe down to every atom's quantum state would require energy and processing power beyond comprehension. But here's the counterpoint. If post-human civilizations exist, their technology might make our supercomputers look like abacuses. And if they are running ancestor simulations, they'd likely hide their presence, making glitches like déjà vu the only breadcrumbs left to follow. The most unsettling question isn't whether we're in a simulation. It's whether time travel's elusive nature is a feature or a bug. If reality is code, then every moment we remember could just be a temporary file, rewritable, erasable, and infinitely replayable. So the next time life feels oddly familiar, ask yourself, have I lived this before, or is someone or something pressing rewind? Here's your next segment. What if the end of time isn't an ending at all, but a beginning? Enter the omega point, a theory so audacious it rewrites not just how time works, but why it exists in the first place. Physicist Frank Tipler envisioned a distant future where the collapsing universe funnels all energy, matter, and even consciousness into a single, transcendent singularity, a cosmic supercomputer so powerful it could simulate every possible moment in history. In this vision, time travel wouldn't require machines or wormholes. It'd be as simple as loading a simulation of ancient Rome or the Big Bang itself, like choosing a chapter in an infinite digital library. At first glance, this sounds like pure science fiction, but Tipler's math ties it to hard physics. As the universe contracts toward its final collapse, computational power would theoretically grow without limit, reaching a point where even human minds could be preserved or resurrected as patterns of information. Think of it as the ultimate backup drive for reality, where time becomes less a river and more a menu of eras to explore. The eerie twist, this idea doesn't just come from equations. It echoes theological concepts of an omnipotent, omniscient endpoint, blending blackboard physics with questions about destiny and divinity. Critics pounce on the leaps in logic. For the omega point to work, the universe would need to collapse in exactly the right way, a fate far from certain given dark energies accelerating expansion. Even if it did, could consciousness truly persist in a maelstrom of infinite density? Some physicists argue that quantum effects near the singularity would scramble any meaningful data, turning the omega point into cosmic noise. Others counter that we're underestimating nature's ingenuity after all. The universe already encodes our memories in the neural webs of our brains. Why couldn't a singularity do the same but on a galactic scale? The real allure of the omega point isn't just its grandeur. It reframes time travel from a technological challenge to an existential inevitability. If consciousness is information, and the universe tends toward preserving information as quantum no-hair theorems suggest, then time's arrow might bend toward an ultimate archive, a place where every moment that ever was or could have been is saved. So is the omega point science, speculation, or something stranger, perhaps all three? It forces us to ask why time exists at all, not just as a measure of change, but as a canvas for meaning. And that leaves us with a humbling thought. If the universe is destined to remember everything, what will it say about us? We've traveled through a universe where time bends, loops, and sometimes shatters entirely, where black holes might hide doorways and particles whisper to their own futures. These 25 radical concepts don't just challenge what we know. They reveal time as a vast, twisting labyrinth, full of paradoxes waiting to unravel and possibilities we've barely begun to grasp. Some may remain locked in equations for centuries, while others could be within humanity's reach sooner than we think. But whether these ideas stay theory or leap into reality, they all share one extraordinary power. they force us to rethink the very fabric of existence. Science thrives at the edge of the impossible, and time travel is the ultimate frontier, one where imagination and physics collide. Even if we never build a working time machine, the quest reshapes our understanding of causality, quantum mechanics, and the universe's deepest symmetries. Every paradox, every hypothetical wormhole, every glitching quantum particle teaches us something new about the cosmos and our place within it. So here's the question that lingers after this journey. If you stood at the threshold of time, where would you step? Would you witness the birth of a star, walk among the dinosaurs, or leap ahead to humanity's farthest horizon? And more importantly, would you dare to interact, knowing the slightest touch might rewrite everything? The beauty of these ideas isn't just in their answers, but in the conversations they spark. Drop your dream destination in the comments. We'd love to hear where your curiosity would take you. And if you're hungry for more mind-bending explorations, hit subscribe. The universe still has endless mysteries to uncover, and we're just getting started. Until next time, keep questioning, keep wondering, and remember, the future, and maybe even the past, is still wide open.